Okay, so let's look at correlation in data points. So for this lecture, we're just looking at, is there correlation? This is an important question to answer. So the setup is we take some data, we vary an x value, and we measure y. And then we can graph it. And the question is, does y depend on x? Is there a change in y when we change x? Many experiments look just for correlation. There's always the correlation versus causation thing, but if you have correlation, you have something. You don't necessarily know the cause, but it's important to find links between different parameters often. So here's an image I took from a poster at an oceanography conference, and it's data that they took, and the big output of this study was whether these two measurements are correlated with each other. So they were looking at the statistics of correlation. Here's a closer look at that poster just for a complete citation. It's by Katie Copeland and Candice Oviatt. I don't know how to say their names. Here's the graphs. And all correlations were significant is one of their major findings. So it's this correlation coefficient R, sometimes capitalized, sometimes lowercase, that we're using. Your eye is a very good judge of correlation. You can usually see the pattern yourself. So trust your eyes, but it's not quantitative, so we need something with some math behind it. R values vary between -1 and +1. 0 means no correlation, a perfect sphere of data or something like that. If your R is 1, that means you have a perfectly linear correlation. If it's -1, it's also perfectly linear but sloping down instead of up. So the questions are, how do we calculate R? Sounds very useful. And what do we call good values? We know 1 and -1 would be good, but what if you get 0.6? Is that good? So those are the questions we need to answer. So here's the equation for the correlation coefficient. We get n pairs of xy data, and we can calculate rxy using this. It's the sum. We need to calculate the averages of x and the averages of y, and then the individual measurements are xi and yi, and they're summed and divided and multiplied and everything together. It's important to eliminate outliers because outliers can have a large impact on this correlation because of the squared value there. So use that Thomson-Tau technique to eliminate outliers first. So now that we've calculated it, what is a good value of R? And the answer, of course, in our class is to use a table. So we have table 6.9 here. And it's a very simple one. If you know n, the number of samples that you have, and the confidence level you're interested in, you can find the minimum R that gives you that confidence level. So it's a table of n, and then the values of R go across for different alphas, which is 1 minus confidence level. So this is 99% confident, 98, and so forth. And you're surprisingly small, especially when you get to large n's, that it can be a significant 99% confident at 0.4 for R. So it's always good to graph and use your eyes as well. XKCD always gets the statistical jokes right. So here, if you can't see where the line should go, be careful because curve fits, which we'll see in the next video, will give you an answer every time. But the correlation coefficient should be pretty small. Okay, so a few examples. So if we took 40 measurements and found a correlation coefficient R of 0.264, what's our confidence level in this correlation? So there's n of 40, and we can read right across 0.264. You might have to interpolate for most values, but we can find we're in the alpha equals 0.1 column, which means a confidence level of 90%. Really simple table to use. Here's an example of calculating the correlation coefficient from some data. This data is exactly linear, so we have x 3, 4, 5 and y 7, 8, 9. They're graphed here in this little sketch. So we should see some strong correlation is the hope. So the first step is to calculate x bar and y bar, the means of the samples, because they come into this equation everywhere. So the average x is 4, average y is 8. Then we can just write out the sums, and so we've got 3 samples. Our n is 3, so we'll have 3 terms in the sum when we sum from 1 to 3, here, here, and here. So we get all of these numbers together, and we find our R value is 1. Okay, so that's it. Hopefully you can use the table to find significant values of R, and you could calculate R and understand what the R value means. Next time we're going to see how to fit the data to find a least squares linear fit.